Good afternoon. So I wanted to, based upon comments in the lab and a few things I've seen, I thought I'd do a little bit of touch-up work on lab 3 here about what needs to be implemented, and then go back to lab 4. First of all, there's in the computational piece of this, there's after the pseudocode, there's a little section here which talks about computing drag, and this is a per computational per frame drag, so you can consider this like rolling friction. The ball is rolling along a tabletop that's has a little bit of carpet on it, and so it loses a little bit of energy on every time step. It's not impact against the walls. It is rather rolling friction. The walls are considered lossless bounces. Secondly, a couple of people have asked me what I think the rate limiting step for the computation is for producing the animation, and that's a hard problem to figure out, but I suspect that for a moderate number of balls, moderate being in the dozens, that the rate limiting step may be the SPI transfer of the position of the balls to the TFT screen. So you're going to have some minimum icon for a ball, and there is a draw a circle, but I don't think you're going to want the overhead of that. I suspect what you're going to want to do is something pretty simple, like build a macro to inline drawing of 5 points, which when you squint at it from far away is a crude approximation of a circle of radius 2. So on every time step, you're going to have to erase every ball and redraw every ball. So the number of points you're going to manipulate on the screen is going to be something like 10 times the number of balls, and each one of those point draws is going to require several SPI transfers, which you can look at in spimaster.h.c. But I suspect that is going to be the rate limiting step. Therefore, it may be worthwhile picking a CPU speed which maximizes the SPI rate rather than the compute rate. Luckily, it's easy to try, because you can just change the prescalers, the phase lock loop prescaler and postscaler quite easily, as we talked about last time. Any questions on that?
Do we have to draw the balls like this, or do we just use a single point?
You can use a single point. That'll save quite a lot of time, of course. You may find there's sort of a trade-off between what looks good and computational speed, and going to a single point is going to make it appear as if balls are bouncing before they actually hit, but probably you won't notice that, because there's increase the radius of a point. Oh, yeah, you can, but then you have to worry about that, the denominator divide, the dividing factor, which I set to be a nice number, a shift number. So there's this very interesting effect, and that is that your effective resolution of your eyes depends upon the speed of the object you're looking at. So for a still image, your eyes are probably good to a little less than than a thousandth of a radian, 0.001 radian or so, probably half that. So you can see maybe 2,000 points at this far away on an 18-inch screen, something like that. If you have an object moving at 1 radian per second across the screen, so that's moving across the screen in 1 second time, your resolution drops below 100 points per radian. So you have a strong velocity dependency of resolution. And you don't notice it because your brain just fills in all the details. Says, it's constant speed or it's constant shape. I know the shape, but you're not actually seeing it. And for a certain number of people who were aficionados of animation in the 70s, there was a thing called a laser disc and had very high resolution, uncompressed single frames of images, and they'd single step through Star Wars, looking for anomalies in the animation, in the CG, the computer graphics effects. And at one point, one of the starships turns into a tennis shoe and shoots off to infinity. And you can't see it at normal speed because your resolution is limited by the speed at which the scene is changing. That's all by way of saying, if you have two balls bouncing together fairly quickly, you can't tell whether they hit or not. So sure, use single points. Another question I got yesterday is, I've been drawing the game field as long horizontally and short vertically, but you've been using the screen in the portrait mode. You know there's a rotation parameter, right? When you do the TFT setup down in main, the very next thing you do after init and begin is set rotation. There's 4 rotation modes. You might experiment with the 4 and see if one of them is easier than the others. Trim pots have gotten a bunch of questions about potentiometers, and my overall impression is you don't use them much in this educational system. Is that true? Yeah. So inside that little square thing with the slot on the top that takes a screwdriver, if we look inside there, what there is a piece of polymer that's wrapped in a circle with a wire at each end. And then there's a piece of metal that can drag along it back and forth. And that's what you're turning when you turn that screw trim pot, is you're moving this piece of metal back and forth along this ring, and that's the third lead. So in the terms of this image, this would be 1, this would be 3, and that would be 2. So, there's 3 leads. Don't hook them up at random, folks. Or, if you are just going to hook them up and pray that they're right, do this. You've got this potentiometer. Now, this is the abstraction of it. One end, the other end, the variable wire. If you absolutely can't tolerate testing it, then put a 100 ohm resistor here and here to VDD and ground, and a 300 ohm resistor here, and then no matter how you hook it up, you can't hurt anything. If these, let's say that you accidentally hooked it up this way with no protection resistors, VDD, ground, A1. So, what happens? You turn this back and forth, nothing's working, you're always reading the same stupid thing, which is ground, but But as you turn the trim pot to this end, now you've taken this piece of metal on 2 and you've run it over to 1 and you've shorted the power supply to ground. Just before you do that, 1 ohm before you do that, just as you're bringing this down to the last point, you suddenly have a very low resistance. All the capacitors in the power supply are still charged, and it blows out the potentiometer. It actually takes this polymer strip and blows a hole in it. And then it doesn't work anymore at all, ever. So think carefully about how you're hooking this up, or put protection resistors top, bottom, and here. All right, so we put, this is a voltage divider. We're putting constant voltages, constant resistors here. How much does that reduce the total range of your voltage? If this is a 10K pot, it reduces it about 2%. Who cares? That'll work. Oh, the last thing is that I've seen at least 2 groups now, maybe 3, hook up the voltage reference code, get the DMA working, blast a series of 4-bit values out to CVRCON, and get no output. And the reason for that is that you cannot blast just the 4 bits out, but rather you have to send the setup bits along with your 4-bit value. You remember that the setup values were 8060, where these 4 bits are the voltage. It turns out that this bit is the on bit, turn on the voltage reference, and these 2 bits enable a pin, the I/O pin, and the other one sets low range. So in the table that you build to spit out of the I/O port, out of the VREF port, in the table you build, you have to build a 16-bit table whose top 12 bits are a constant and whose low 4 bits are the signal that you want to send. So the table is going to be a very boring table of 0860 and then 4-bit values. There was another question about that using my DMA code, the system kept playing forever. And the reason is that the first DMA example, the first DMA code example, assumes that you want to produce a sine wave forever. And so in particular, when the system was set up, when the DMA was opened, it was opened in mode auto. Mode auto means never consider the block to be done, but always restart it forever. You don't want to do that. For this lab, if you want to play one beep and then have it quit, you need to open it in mode normal. Right. Which happens to be the default, by the way. Then, of course, you have to give it your table name. You have to do a set transfer. Give it the table name, the I/O port name, which for you is going to be a void pointer to CVRCON. The sign table size, the target size, and what is your target size going to be? How many bits in CVRCON? 2. How many bytes per cell event? 2. Because you need to transfer a 16-bit value to the port, to the register. The rate, to remind you, the rate at which you play through the table is going to be controlled by a timer overflow, but you're not taking the interrupt. You're not writing an interrupt service routine. An interrupt service routine to play this will cost you points. You are telling the DMA channel to use the timer interrupt flag, but don't enable the interrupt. Do not enable the interrupt. Any other questions about Lab 3? By the way, this is how you calibrate the clock. Folks, don't do this unless you really, really want to do this. It turns out that changing the clock is such a critical thing that you have to do a bunch of black magic here before you can do it. You have to write to a one register on successive cycles with some very odd codes. These are meant to be bit patterns that are hard to get at random. They mean nothing else except that they're hard to get randomly. Then you write the register tuner, and then you give it a sys key 0. Don't do this unless you absolutely feel obsessed with high accuracy sound. There's no reason to do that right now. But it can be done. Any questions about Lab 3? So how many people have noise coming out of the VREF port? 1, 2, 3, a few. That was a maybe? I'm not sure. It made some noise, right? And how many people have got balls colliding on the screen? Okay. Let me remind you that lab will be open on Tuesday, should you care to skip fall break. All pumped up. Andrew may open it on Monday, but he's not sure yet. One of the TAs. Okay. Anything else on Lab 3? Let's go back to Lab 4, talk a little bit about serial stuff. So, Lab 4, as we talked about last time, introduction to Lab 4 last time, is a motor controller. We're going to ask you to use a serial connection to the PC. So this is a very old protocol, but it's still used because it's simple. So the PIC32 is going to use 2 pins to to communicate with the outside world through a device called a USART, a universal asynchronous receive transmit. So there's going to be a TX pin, which is pin 21, and an RX pin, which is pin 22. There's actually a pair of pins, and those are all on PPS, but pins 21 and 22 are special. And the way they're special is that they are 5-volt tolerant. So if you look at this diagram of the pinout of the chip, you'll see a few of these pins are grayed out here. The reason they're grayed out is to indicate that they can tolerate a 5-volt input for a 3-volt system and not blow up. So in particular, pins 21 and 22 are 5-volt tolerant. And that matters because of the two kinds of adapter cables we have. One of them is a 5-volt system, left over from the bad old days of AVR. So this produces a 5-volt signal, and so you must run these to pins 21 and 22. If you use the other pins, it blows up the chip. This adapter is a 3-volt part. And so you don't have to connect it to pins 21 and 22, but if you want to use the default code, you are going to. And up until this generation of PCs in the lab, we ran level shifters because the old standard for RS-232 signaling, so the signaling coming out of here is ASCII signaling, ASCII encoding of characters, and I'll explain that in detail in just a minute. And then, so that was ASCII encoding, and then the levels were shifted to RS-232 levels, which for various historical reasons are +5 and -12 volts. And that's what the PC expected, but nobody uses a serial port anymore. Most of your laptops don't have a serial port on them. So what we're going to do now is to run these into a TTL level serial to USB adapter, and then run the USB cable over to the PC, where we're going to run the PuTTY terminal. P-U-T-T-Y, where TTY is uppercase because PuTTY emulates a hardware terminal called a VT100. You can Google it up. There's a certain number of people who consider the VT100 the height of technological innovation in America. And the VT100 emulates a teletype, which is an electromechanical machine from the 1900s, early 1900s. So what you're going to get here is a console window, a serial console window, with which you can communicate back to the PIC32. So we're going to ask you for this lab to be able to issue typed commands from the PC keyboard into the console window for the PIC32, have the PIC32 then set variables based on the console that you're running on the PC, and perhaps echo back information for debugging and for other uses back to the PC. This is a clockless system. There's a transmit line and a receive line, and of course ground. But there's a transmit line and a receive line. These are both data lines. There's no clock line. It's asynchronous. So how does the system work? Well, what's going to happen is this thing sits at VDD, the transmit line, TX line sits at VDD. When the PIC32 is ready to send a character, it drops this line to 0 and holds it there for 1 bit time. On this edge, on the other end in the PC, the clock starts. So that edge phase locks the transmit clock with a receive clock. Then the next 8-bit times send data from least significant bit to most significant bit. And then there is a stop bit, which is 1 bit long and is high. To make sure there is clock synchronization, so it's 10 bits total. 10 bits total to send an 8-bit character. And to make sure that there is no clock skew, this architecture, the PIC32 architecture, samples each bit 4 times, and they all have to match during the bit time. So each bit is sampled 4 times. And because there is no clock transmitted, if we're going to have 10 bits, each one of which is sampled 4 times, the maximum clock skew between the transmitter and the receiver cannot be greater than 1/40th of the character time, because that's the number of sample times within the character. Therefore, the clocks have to match within 2.5%, which is 1/40th. And as you know from Lab 2, the resonator, the internal resonator, is good enough to do that. It's actually 0.9% or so. But you must set up PuTTY so that the clock rate on PuTTY matches the clock rate on the PIC32. What is the clock rate on the PIC32? So let's go back down to the proto-threads page. And I tried to package this up to make it a little bit easier to use. But if we go to config.h, we'll find that there's 2 parameters for the serial pins. There's a use UART serial, which you are going to define for this project because you need to turn on the UART serial. And there's a baud rate. Baud rate is an old term for bit rate, and it's 9,600 bits per second. So you must set up PuTTY to run at 9,600 bits per second. Or, of course, you could change this parameter. If you decide that you can read more than 1,000, so 9,600 is 960 characters a second. If you find that too sluggish, if you find that too slow for your fast reading ability, speed it up. But you do have to have them match. And the symptom will be, if they don't match, the symptom is random characters. It doesn't fail, it doesn't give you an error message, it just prints garbage. Any questions? So I tried to give you some print utilities to use in the header file. There's send string and receive string, and the reason I had to write those is that printf and scanf, the standard CIO library, is blocking. And a scanf in particular will block forever if the user doesn't type and enter. So for a multitasking system, that's not appropriate. And what we need to do is to make the I/O system, the serial I/O, non-blocking. So when it's waiting for a character for the UART to receive a character, the thread has to yield to another thread so that it can go and do something useful while waiting for the user to do something. So there's a couple of levels to this. First of all, we have to physically turn on the UART, and this code is protected by an if-def use UART serial. So when you define that in the header file, what you're really doing is turning on a stanza here that initializes a bunch of I/O stuff. In particular, it takes over pins 21 and 22 for the physical interface for the transmit and receive lines. It configures the UART to enable the transmit and receive pins. It sets the data size. It sets the baud rate. It enables it. And it defines a DMA channel, channel 1, to use for outputs. So if you define UART serial, you can't use pin 21 and 22 for anything else besides serial. And you can't use channel 1 for anything else. Channel 1 of the DMA for anything else. Again, the DMA is set up to be in match mode as opposed to auto or default. So when you're sending a string and you get to the 0 representing the last the end of the C end of string, the DMA set match pattern, when it gets to a 0, it turns itself off. It ends the burst. So there's a big setup block here that hooks up all of the I/O. And then there's another level which tries to hide some of this gross stuff from you. So there's a function, get serial buffer, that fills a term buffer with characters that the human types. And it's written as a thread so that you can spawn the thread and wait for it to return when the human says, presses the enter key. So we're giving it a max care limit. That's to avoid buffer overrun attack. Not that you're going to attack yourself. But we want to make sure we never wait for the UART. Because the UART at 9600 baud is going to take 1 millisecond to get a character. That's 40,000 cycles wasted if you wait. So what's going to happen is, as soon as we get in here, we're going to yield until the received data is available. We're going to yield the thread. We yield this thread. This thread is spawned by another thread. So that thread is stalled. Both threads are stalled until UART2 has data available. Then we read it using UART get byte. That's easy. Then we yield until the transmitter is ready. and then we send it back. Why do we do that? The reason is, by default, when you press on the keyboard over here, boink, nothing appears on the PuTTY screen until it is transmitted over to the PIC and the PIC echoes it back. So this functionality here with transmitter ready and then send byte character implements echo. And character echo is a way of guaranteeing that the data got to the PIC and back again. So it's kind of crude rudimentary error checking. I implemented an erase function, a backspace, but sadly, not every keyboard uses the same key code for backspace. My key combination on my computer happened to be 7F, but I don't believe that's universal. So this commented out piece of code right here, this printf %x --car, gives you the hexadecimal equivalent of backspace if you press the backspace key. So that you can change that define in the code. But if it's then we go into the parser here and say that if we're at the end of line, if there's an enter which used to be called return for carriage return because the physical teletype printer head moved back to the left side of the paper. This is a mechanical device, remember, impact printer. So carriage return. Then we're going to write a 0 because that's the end of string. We're going to wait until the transmitter is ready. Then we're going to send a new line, which is how PuTTY signals a carriage return, an enter. And then we're going to break and go back to out of the while loop. Otherwise, if there's a backspace, we got to do a bunch of stuff to fix the bad character and move the position back on the screen and do a bunch of other stuff. But in every case, it waits until the transmitter is ready so that we never block even while we're waiting for a backspace to occur. When we finally get to an enter, we do an exit, the thread exits, and we go back. To send a string, somewhat easier really, we do a put serial buffer. We give it the number of, we enter with a string. We wait until, as long as the contents of the string at the first location is not 0, or at the location is not 0, we wait until the transmitter is ready. We do a send byte. We increment the number of characters to keep track of this internal index. And we get to the end, we exit. But that requires a yield on every transmitted character, and that seemed like too much overhead. Besides, I was trying to play with DMA and figure out how it worked. So made an alternate, which is PT-DMA put serial buffer. And in this case, we check first to make sure there's actually data, and if there's not, we get out of there before we try and DMA burst through memory forever. We wait till the transmitter is empty. We send one character. And while that character is being sent, we enable the DMA channel. We enable the DMA channel, and then we yield until the DMA channel is done with the entire burst transaction. Because now, once you've enabled the channel, and you've set up the channel to transmit until there's a compare match with 0, it sends the whole string. So as long as you use the high-level commands, put serial buffer or get serial buffer, then all of the gross details about transmitting and receiving strings is hidden from you. And that's what you're going to want to do for this lab. There's a couple of examples. There's a keyboard thread control. This example, I don't know why I did this, because I violated one of my own rules, which I hate. I'll fix it when I get the chance. So I'm defining a string, a little command prompt, CMD arrow for a command prompt, and then bouncing it out to PT DMA put serial buffer. It spits it out to the terminal in DMA mode, returns this thread, and then does a PT input, a PT get serial buffer, and waits until that spawn doesn't return until the human hits enter, and then we do a scanf, scanf, to decode this into a command and a value. That's all good. Then there's a command decoder which says, if the case is T, I wanted to do one thread, and if it's B, I wanted to do something else. But for P, down here for print the time, I used a printf. That's blocking. I have no idea why I did that. It should be an scanf followed by a put string, PT put string. And my only guess is misfiring. Brain misfiring, that is. So you don't want to use printf ever on your command interpreter, because it will block, for this lab, it'll block the string which has to control the motor. And during the time the printf executes, you could have the motor over rev or under rev. As an aside, the transmit receive hardware on the PIC32 is yet another small coprocessor. When you push a byte into the transmit register, when you tell it to transmit, a separate piece of hardware then fires off a clock and starts shifting bits out of a shift register for you in hardware at the predetermined rate, at the baud rate, until it's done, and then stops. But there's actually more. There's actually a FIFO buffer on the output and a FIFO buffer on the input, and this is full duplex, so that you can transmit and receive at the same time, as long as your software supports getting the characters in time. So the hardware is full duplex. So one task you should do for lab 3 is lab 4 is get the serial running. Another task is for one person to build the motor control, and a third task is to build the sensor. So there's a sensor circuit, there's a motor control circuit, and there's a serial control thread that are almost independent to get working. So if you have 3 people, that's obviously 3 people's work right there. Probably do it all in one afternoon. Then you got to integrate it, of course. So any questions? The serial stuff, there's a lot of stuff churning under the water level. There's a lot of paddling going on, but at the at the threads level, at the PT threads level, you're going to do a put serial buffer or get serial buffer, and that's really all you have to do. When I get good enough at this version of GCC, I'll rewrite put car and get car so that printf and scanf just work the way they should, but I haven't gotten there yet. It'll take me a little while to do that. Final projects. Next week. Next week in lab. Need your proposal. So, 1 week from today. Yes, Wednesday. 1 week from today for the Tuesday and Wednesday people. You need a 2 to 5 page proposal on what you're going to build. Small reminder. Any questions on that assignment? What should be in there, what shouldn't be in there? Well, Piazza will be working all during break, and I'll be reading it sporadically. I'm going to, on Saturday afternoon, I'm going to geek it up and run a station at the Schuyler County Solar Tour. So we have people visiting my house and looking at solar power systems and hopefully not fiddling with the inverter parameters too much. But aside from that, I'll be around most of the weekend reading mail flow. See you in lab. I'll be in lab all afternoon today.